Not right now. Alright, I can start now. Alright, so today we're going to be talking about DFS Lowlink. For those of you who aren't aware, DFS Lowlink is an algorithm we use when working with special types of connected components. I'm sure everyone here has worked with connected components before, because if you've worked with the DSU, you've worked with connected components. But we're going to be looking at a few special kinds of connected components. The first kind we're going to take a look at is referred to as two vertex connected components. I will use CC as an abbreviation for connected components because it's easy to write that line. Sometimes you'll see two of these types of connected components grouped together as biconnected components. But when talking about these types of components, it's very important to be specific about which kind you're looking at. In the case of two vertex connected components, a two vertex connected component is a component of a graph such that any node that's removed will keep the graph intact. So if we were to remove this node here, the graph is still connected. And so more specifically, we can say that this whole section of the graph is a two vertex connecting component. Because any vertex we would remove from this component, or from this part of the graph, will keep the graph fully connected. However, if we were to look at, say, this whole component here, this does not hold true. Because if we look at this node here, removing this node would disconnect our graph. We have a special name for this type of node. If removing a node disconnects the graph, we call this node a articulation point. You will also sometimes see these referred to as cut vertices. In addition, we have two more cut vertices in this graph. We have these three nodes here are all cut vertices. Does anyone have any questions about what a two vertex connected? Oh, yes.
Yeah, so for the connected components, is it like connected if, I don't know how to explain this. Like if you have like a ring of nodes, right, and you remove any one of them, it'll still be connected. But if you remove any two of them that aren't adjacent, then it'll be disconnected. Would that still be like a connected component?
So two vertex connected components are specifically if one vertex is removed and it keeps the graph connected.
Okay.
If you remove, like you can remove two and like have a disconnection there, and that doesn't affect that. If for any pair of nodes we remove those pairs and it stays connected, we call that a three vertex connected component. Those are much harder to work with.
And they also show up less.
Yeah, I've seen like maybe 2 or 3 problems, and usually it's like not meant to be solved.
Okay. Thank you.
So now we need to talk about how are we going to find these connected components. First, let me give these nodes labels. We are going to start by constructing our DFS tree. So if we start at 1, let's see if this graph, does this graph give an interesting DFS tree? I think so. So we start at 1, let's DFS to 2. We'll DFS to 5. 5 can DFS to 4. 4 can only go back to 1. And we'll label these edges as a special type of edge. Whenever we revisit a node, we'll label that as a back edge. I'm not going to draw all of these in yet, but those will be important later. So 5 can DFS to 6. 6 can DFS to 7. So this is our DFS tree for the current graph. And we're going to introduce two terms here. There is going to be our pre-order and our Lowlink. When working with DFS Lowlink, the pre-order is going to refer to the first time we enter a node. So for 1, our pre-order time will be 1. For 4, our pre-order, or sorry, for 2, our pre-order time would be 2. Pre-order of 5 would be 3. Pre-order of 4 would be 4. Pre-orders of 6 would be 5, and so on. Our Lowlink is going to help us describe this concept of escaping. Essentially what we want to say is a node's Lowlink value will be the largest pre-order any node in our subtree can reach. So like if we looked at 10 for instance, 10 could DFS to 11. 11 is in the subtree of 10. But because there's an edge connecting 11 and 5, 11 can reach a pre-order of 3. So that means 11's Lowlink would be 3, and 10's Lowlink would also be 3. So essentially what Lowlink tells us is how far up our DFS tree can we escape to. Yes?
We're using only one iteration, right? Like, you can't, like, go back edge, down, back, another back edge.
Yeah, correct.
Like, how far you can escape using at most one back edge, I think, is that
Yes,
like
I believe that's true. Does anyone have any other questions about pre-order or Lowlink? Yes, Brigitte.
Would the pre-order of 4 not be 1 because there's a back edge to 1 with pre-order 1?
No, pre-order is just when did we enter this node in our DFS.
Okay.
So essentially we can view it as like when we're DFSing, keep a global timer. We will increment this every time we visit a new node, and whatever that time is when we enter that node becomes our pre-order.
Okay.
So just to finish filling this out now, we have so 1 is the first node we enter. We'll always give it a pre-order of 1. We'll always initialize a Lowlink to the pre-order value as well, because we can always escape. Like we can always see our own pre-order. 2's pre-order will now become 1. Lowlink will be 1. So this is equivalent to saying we DFS to 2. We DFS to 5. 5's pre-order is 2. Lowlink is 2. We go to 4. And we say that 4's pre-order is 4. And 4's pre-order is 4. But now, when we are at 4 and we try DFSing, we're going to try visiting this edge here. As previously mentioned, we call this edge a back edge. Whenever we try to take a back edge, we can now update 4's Lowlink to say, hey, 4 is going to try reaching 1, but we've already seen 1. So we can update our Lowlink with the pre-order of 1. So 4's Lowlink is 1. We finished DFSing down this branch now. So now we're going to go back, we're back at 5, and we're going to consider our next DFS. But before we continue DFSing, we can say, oh hey, our child found a lower Lowlink value. Let's update our Lowlink. Our Lowlink is now currently 1. Yes.
Why is 4's pre-order 4 and not 3?
Because it should be 3. That's my bad.
Since Lowlink should be 0, right?
Yes. 4 escape to 1. I used 0 versus 1 indexing in 2 different positions. That was my confusion. I'm working 0 indexed here. Earlier I had talked about pre-order as 1 index. It doesn't matter which one you use as long as you're consistent. Since I already started filling out the pre-order 0 indexed here, I'll keep going 0 indexed. So 4's pre-order should be 3. 4 has a back edge back to 1. 1's pre-order is 0. So 4's low link should be 0. 5 will min its low link with 4's low link. So 5's current low link is 0. Does anyone have any questions about that?
Does 2's Lowlink also become 0?
Not yet. We need to worry about, we're going to keep DFSing, and we only update it when we are done fully traversing our subtree. Does anyone have any other questions before I continue? Alright. So we're back at 5. We have DFS down 4. So we're going to continue DFSing now. We're going to visit 6. 6's pre-order value is going to be 4. And we're going to initialize 6's low link to 4. Now, 6 is going to traverse to 7. So 7's pre-order is going to be 5. Low link's initially going to be 5. Same thing with, now we traverse to 3. Pre-order is 6. Low link is 6. We traverse to 9. Pre-order is 7. Low link is 7. And then we traverse to 8. Pre-order is 8. Low link is 8. But now, 8 has a back edge to 7. So we min our low link with the pre-order of 7. So our low link becomes 7. Or sorry, our low link becomes the pre-order of 7, which is 5. So our low link becomes 5. We finish DFSing here, so we go back to 9. 9 has nowhere else to DFS to. So, and we're going to update its low link to 8's low link value, which is 5. We're done DFSing at 9, so we go up to 3. 3, we're going to update 3's low link to 5. And then we end up at 7. 7's low link is already 5, so we don't update anything. Anyone have any questions so far? Alright, I'm going to take a break here because we have something special that happened. We have fully traversed 7's subtree. And we have ended up with a low link value equal to our pre-order. This is a very special case because what we have just found is that no node in 7's subtree can escape past 7. The highest pre-order we can reach is 5. Therefore, 7 blocks everything else from being in our, or 7 blocks everything from reaching a higher value, which means that 7 is an articulation point. So because we have reached a spot where our low link is equal to our pre-order, that means we are at an articulation point. Does anyone have any questions about that? Alright, so we'll continue DFSing. So, we're at 6. 6 is going to DFS now to 10. So its preorder is going to be 9 with a low link initially of 9. We DFS to 11 with a preorder of 10 and a low link initially 10. 11 now has a back edge to 5, so we can update low link to be 5, which means 10's low link updates to 5.
It should be 2.
Oh, yes. So low link updates, 10's low link updates to 2, and 6's low link updates to 2. So I think I messed something up.
I think so. Like, I mean, 5 is an articulation point and also, like, part of the original.
6 also is.
Yeah,
Six
but
is on too low.
I think I've been describing the wrong version. Because okay, so what we're finding here is that 5 and 6 allow us to escape further. We're actually what's being described here actually describes a different type of connecting component. So quick detour. We also have 2 edge vertex components.
2 edge vertex.
And a 2 edge connect component. It's the same idea as a 2 vertex connect component, but for every edge, if we were to remove it and the component still stays fully connected, then it's a 2 edge connecting component for any edge in that component. So, and when we have an edge that disconnects a graph, so if, like, let's say, for this edge here, removing this edge would disconnect our 2 different components. We call this edge a bridge. So, also, as earlier, articulation points have the alternative name of cut vertex. Bridges have the alternative name of cut edges. And one thing I should have specified earlier, and this is where I had messed up earlier, is that when we work with 2 edge connecting components and 2 vertex connecting components, we view them slightly differently. We consider a 2 edge connecting component to be a subset of edges, of nodes. So if we look at the subset of nodes 7, 3, 9, and 8, we call this subset of nodes, this subset of nodes a 2 ECC, a 2 edge connect component. With vertex connect components, however, we view them as subsets of edges. So if we looked at the edges 7, 3, 3, 9, 9, 8, and 9, 7. This subset of edges is a 2 vertex connecting component. So, with this algorithm I've been describing here, we've been focusing on the nodes. And because we're focusing on subsets of nodes, what I've been describing has actually been the algorithm for finding 2 edge connected components. So, what we found here is that
The incoming edge to 7 is like bridge.
yeah. So what we have found here is that no node in this subtree can escape higher than 7. Therefore, all of these edges we have seen in this subtree, including the back edge from 8 to 7, form a 2 edge connecting component, or all these nodes form our 2 edge connecting component. So now, as we update our low links going up, we don't see another case of pre-order and low link equaling each other until node 1. In this case, now we have that.
There's node 2, you haven't updated the lower.
Oh, yes. As we DFS up, 2 finds that 5's low link was 0, so we can update our low link value for 2 to 0. So, because nothing can low link past 1, that must mean that the remaining nodes form another 2 edge connect component. And what that means is that the edge connecting 6 to 7 must be a cut edge. Does anyone have any questions about that? Yes.
With the mix-up, when you were first describing how we found that, I think you said that, not 7, you said that 5 wasn't, no. I forgot which one you said was an articulation point.
So in this graph, 5, 6, and 7 are all articulation points. The only cut edge we have, though, is 6 and 7.
Oh, sorry, yeah, you said that 7 was an articulation point. So now you're saying, like, with this new algorithm, you're saying that the edge, okay, between
Yeah.
6 and 7 was...
Yeah. So the issue was that the algorithm I'm describing currently does not find cut vertices, they find cut edges.
Okay, so when the pre-order is equal to the low link, it's the edge leading to that node?
Yeah.
Okay.
Yeah, so if after I finish DFSing to all of my children, my low link ends up equaling my pre-order, that means that I have found that I am starting, I have formed a new 2 edge connecting component. And in order to implement this, what we can do is as we DFS through our graph, we will maintain a stack of nodes we visited so far. When we find that our pre-order is equal to our low link, we will pop all nodes from our stack until we reach ourselves. So,
Now there's a question.
yes.
This stack, is this like something you like have to specifically implement, or can you use like the call stack and recursion for this?
So we're already using recursion for the DFS, so we would have to use another stack in addition to this.
Okay.
So as we DFS, we would add our nodes to the stack. So once we DFS up through 8, we start back propagating until we get to 7, and we see that 7's low link is equal to its pre-order. So what we can do is we'll say pop from the top of the stack, and whatever subsegment we get until we reach the node we're equal to, this section will equal a new 2 edge connecting component. So we would say pop from the stack 8, 9, 3, and 7. And this forms a new 2 edge connecting component. And now we can continue DFSing. I skipped over 5 at some point, which isn't great.
Or, no, it was already there. The third one from the bottom.
Oh, I'm okay. Never mind. I'm blind. So we DFS'd all the way to 11. Now we're working back, and we reach 1. We find 1's pre-order is equal to our low link, so we can now pop until we see 1 to form our new 2 edge connect component. So essentially, we're maintaining 2 stacks.
Forgot two.
But yes,
You forgot 2. And that was.
What?
No 2 is not in your set.
Oh. So the general idea to form 2 edge connect components is we'll DFS and maintain our low link value. We initialize our low link to our pre-order. As we traverse each of our children, we will min our the low link value our child gets with our value. Anytime we see a back edge, i.e. the edge leads to a node we've already visited, we will update our low link value with the pre-order of that node. Essentially, one way you could view it is that we're kind of doing like a tree DP on our DFS tree. Yes.
Is it true that this is implying that I guess kind of intuitively, that the set of bridges is exactly the edges that span 2 cut vertices?
Yes. Or no. Because 5 and 6 are cut vertices, but the edge connecting 5 and 6 is not a
Oh,
bridge.
it's, okay, so it's sufficient analysis.
Yeah.
Okay.
It's the other way around. This is a bridge to, like, the nodes connecting a bridge are cut vertices.
That's also not true.
Is it not true?
If I give you a graph like this, actually,
It is true.
It's true.
okay, it's
It's just
true,
edge
but I
cases.
think there's like some stipulations and
Yeah,
definition.
there's
just
definitely
a
some
different way.
weird, like, edge cases.
Yeah, like,
But I think it's generally true.
yeah.
Well, that first one isn't a cut vertice, isn't it?
Oh, I think that's what it is. Yeah, like this isn't an articulation point. This one is, but this is still a bridge.
Yeah.
That's like the weird case. Alright, does anyone have any questions on this?
So are you? This is the algorithm to find 2 edge CC.
Correct.
Are you also going to show us 2 vertex CC or?
Yeah, so for this one, the idea is that we need to slightly modify our approach. I wish I had Control Z in real life. Essentially, we're going to back up a little bit. Because now that we are dealing with 2 VCCs, which are sets of edges, we are going to slightly adjust our algorithm. What we're going to do, first off, the first major change we're going to make is instead of pushing nodes into our stack, we're going to push edges into our stack. The way I typically implement this, just as a heads up, is I will assign IDs to edges, and I'll push those IDs into the stack. So, we are going to maintain pre-order and low link the exact same way.
Let's see.
That works not great. So far I have added, or I've traversed the edges 1 to 2, 2 to 5, 5 to 4. And one important note to make, when we maintain this stack, we do also want to keep track of our back edges. So in this case, 4 to 1 would be a back edge, and we visited it, so we want to make sure to add that to our stack still. So 4 has a back edge, so we update its low link. 5's low link updates. Alright, so we've reached 8. Just to add in the edges we've seen now. Alright, so we're at 8, we take the back edge to 7, update our low link value. So 8 has the pre-order of 8 and low link of 5. We update 9's low link to be 5. 3's low link to be 5. 7's low link to be 5. And then now, now what we can see is we are going to consider this edge here. Once we get here, we see that the low link of our next node is equal to our pre-order. When we reach this case, we are now going to say that this edge must be a part of a 2 connecting component, because every node below us can reach up to 7. So we say that this edge starts our new 2 VCC. So we'll say take all nodes until we see 7-3, or sorry, all edges until we see 7-3 in our stack, and create a new 2 VCC from that. So all of these edges form our new 2 VCC. We pop those from the stack. And because we did this, we can mark 7 as a articulation point. Does anyone have any questions on that part? So the key idea here is when we have an edge, U to V, such that V's low link is equal to U's pre-order, we're going to start a new 2 VCC. So to continue, we continue from 7 now. And we go back, so we go back to 6. And stipulation. It's not just equal to. It's if our low link is greater than or equal to. So
Does this also apply to 2 edge?
no. This is specifically for 2 VCC. Because if we look at this edge here, the low link of 7 is 5, but our pre-order is 4. So that means that through this edge, there is no way of anything in our subtree getting back to 6. So that means that cutting out 6 will disconnect this section of the graph. So, because the low link of 7 is greater than or equal to 6, we can form a new 2 VCC, which is going to be the lone edge of 6, 7. Shut up. So, the core idea here is a 2 vertex connecting component occurs whenever we have an edge whose second node has a low link that is greater than or equal to our preorder. Whereas with a 2 edge CC, we start at 2 edge CC when our low link is equal to our preorder. Does anyone have any questions about that? There is one thing to be really careful of here, and that is starting your DFS at a cut vertex or at a cut vertex. In this specific case, like if we were to start at 5, actually, for this case, I'm going to work with a little bit of a simpler graph. When working with these types of problems, one good graph to always look at is the bow tie graph. We refer to the bow tie graph as 2 triangle graphs connected at a single point. The reason this one is good is because this is an example of a component that is a 2 edge connected component, but is not a 2 vertex connected component. So if we look at this case, and let's say the center node is our 1 node. In our DFS tree, we start at 1. We go to 2 and 3. We go to 4. We go to 5. The important thing to note here is that it doesn't matter what happens with our low link. For whenever we see an edge, or whenever we work with 1, what's going to end up happening is that once low link is always going to be 0. There's no value less than 0. There's no whatever node we start at is always going to have a low link equal to its preorder, which means that we might erroneously mark an edge as a cut edge that isn't actually a cut edge. So when working with developing like these types of algorithms that use DFS Lowlink, it's always important to keep in mind what is your starting node and make sure that you handle those nodes correctly. I will post some code in the Discord after the lecture today that shows how to properly handle this edge case. Does anyone have any questions? Yes.
For in the previous one where we're going through and we're keeping the sets of edges, is the cut node always the yield first edge? Is that the case?
Yes.
Okay.
Yes, except for no, I think this edge case is fine. I think that should always be true. Does anyone have any other questions? So there's one more type of connecting component I want to talk about today, and that is in relation to directed graphs. So both 2 VCCs and 2 ECCs are only defined on undirected graphs. When working with directed graphs, we instead work with a different type of component called the strongly connected component. A strongly connected component in a directed graph is a component such that every pair of nodes have a path between them. So if we look at an example, in this graph, we have the following sets of nodes are strongly connected components. To iterate, before we mentioned how what we define the set on is important for two VCCs and two ECCs. For strongly connected components, or SCCs, we always define SCCs as groups of nodes. So, if we look at these examples here, let's take a look at the top left example. Every pair of nodes here, if we look at every pair, there is always a path from both U and V and V to U. So that means that that component must be a strongly connected component. But if we look over here in this section, this node here can't reach either of these two. So this is this node by itself is a strongly connected component, but it has no other nodes in its component. Does anyone have any questions about strongly connected components? So the big so we can use DFS Lowlink once again to find strongly connected components, but there is one major consideration we need to have. With the previous two algorithms we talked about, a big implication was that every node, every edge that we take is either going to be a part of our DFS tree or a back edge. And that is only true because of the graph being undirected. In this case, what can happen is, let's say this node here is node 1. We start DFSing, and we would only consider this portion of the graph. But when we consider now DFSing from, let's say, like this node, we've already processed this section. So when we consider this edge here, this edge it's technically a part of our DFS tree, but we've already processed this section of the graph. So we don't want to update our Lowlink using this section. We could erroneously say we visited an earlier node by referencing this section using this edge. So instead of just working with our classic scene array for a DFS, we are going to have nodes be in one of 3 states. So in our scene array, scene of U will be 0 if we haven't seen this node at all. It'll be 1 if it is currently in our DFS stack. And then it'll be 2 if we have fully processed this node already. So now, we'll once again start DFSing. We'll say the pre-order of this node, or we'll do the example here where I start here, say this pre-order is 0, this low link is 0, we DFS here, pre-order is 1, low link is 1, pre-order is 2, low link is 2, pre-order is 3, low link is 3. But then 4 can go back to 1, that's a back edge, so we update our low link and work backwards now. And we find that our pre-order of 1 is equal to our low link of 1, so that's going to be a strongly connected component. This uses the same condition mentioned earlier of if, yes.
Okay, I'll let you finish because this is kind of unrelated.
So we're going to use the same condition mentioned earlier for 2 ECCs of if our pre-order is equal to our low link. But now, we say that for each of these nodes, we finish processing these, so scene of 1, 2, 3, and 4 are all equal to 2. Let me draw out the array just so that it's a little bit more concise. So currently, we've seen 1, 2, 3, and 4 and fully processed them. Currently, we've seen none of the other nodes. So now we will start DFSing from 5. 5's pre-order will be 4 with a low link of 4. 6's pre-order will be 5 with a low link of 5. 7's pre-order will be 6 with a low link of 6. And then now we try DFSing down to 1. But also, because we visited 5, 6, and 7, we'll update each of these to 1. To say that 5, 6, and 7 are all a part of our current DFS. That's what the 1 state essentially means. But if we look at 1 now, 1 has been fully processed. So what we're going to say is that we do not want to update our low link if the edge we're considering brings us to a node who has already been fully processed. But 7 connects to 5. So this node connects 2 nodes that are currently in our DFS stack. So we will update the low link of 7 with the pre-order of 5. So our low link will be 4. 8's pre-order will be 7 with a low link of 7. 9's pre-order will be 8 with a low link of 8. And 10's pre-order will be 9 with a low link of 9. Now we're going to pop 10. So now we're done processing 10. 10's low link is equal to its pre-order. So we mark 10 as a strongly connected component. So far we have that 1, 2, 3, and 4 is a strongly connected component. And 10 is a strongly connected component. 8, 9, and 10 are all DFS to currently. But we have just finished processing 10. 10 no longer connects to anyone else, so we're done DFSing through 10. So we mark his value as a 2. 9's low link is equal to our pre-order. We have a new SEC. So now, 9 is a SEC. We're done processing 9. So 9 is going to now be marked with a 2. And then now 8. We DFS from 8 to 9 already, but we still have the edge from 8 to 10. 10, however, is marked with a 2, so we don't want to update our pre-order here. So we're done processing 8. 8's pre-order is equal to our low link, and we have a new SEC. And then we mark 8 as a 2. We go back to 7. 7's done. 6 is done. And we're back at 5. 5's pre-order is equal to our low link. So we now have that 5, 6, and 7 are a SCC. Yes.
Okay, so for the scene array, could you also hypothetically do, instead of like updating it to 2 once it's out of the stack, could you just like set it to like which initial DFS call did I visit this node on?
Are you saying to like maintain like the SCCs, or what do you mean
Like-
by that?
As in like if, because like presumably it's only a problem if like you call the DFS on one and then you're not done visiting the rest of the nodes, so you have to call the DFS on another node. Can't you just check if I first visited this node on an earlier DFS, then I just don't go to it?
Yes, but you might need to maintain negatives then, because 0 and 1 could be like IDs of nodes you've DFS from. I think what you're saying would work. I think it's safer to use 0, 1, and 2 though.
Okay.
Does anyone have any other questions? Yes.
When you draw an SCC that's not a cycle,
Yes. Every SEC will have a cycle, like naturally in it.
yeah, but like not only a cycle.
So like, this would be an example of an SEC. We could also like,
Only the
oh, I flipped an edge.
Like, once you have a cycle, you can add edges arbitrarily.
Yeah.
It doesn't really matter.
So like, this is an example of an SEC. Yeah, SECs don't just have to be cycles, but they will be composed of cycles. Like, there will be at least some cycle in an SEC by definition. Yes.
So once you like go back to a node and then find that it's like the P is equal to the L, can you be confident that you've visited like everything that's in its connected component is on the stack?
Yes, because you would have had a DFS to everything in its connecting component. Because by definition, a strongly connected component has to have every path between U and V and V and U for all pairs U and V. So if that's true, then we must have DFS to it in this iteration.
Okay.
Any other questions about this? There's one last thing I would like to talk about quickly. But before we move on, does anyone have any questions? Alright. So there is one specific manipulation that is worth talking about here, and that is the idea of metagraphs. They're sometimes referred to as condensation graphs as well. So the idea with these connected components is sometimes we will have properties that we can say are equivalent throughout a connected component. And what we can do is we'll say, for each connected component, for each strongly connected component, create a meta node that represents that connected component. For the sake of this example, I'm also going to add an edge from 4 to 9. However, note that this does not connect what our connected components are. And what we can see is if we view this new graph, where we only consider connected component, the condensed nodes, then what ends up happening is we have a property that we can manipulate for a lot of problems. And that is that this graph cannot contain any cycles. This condensation graph is going to be acyclic, and that allows us to do things like run VPs on this new graph. Yes?
Notably, the algorithm also does return, like, it processes the components in reverse topological order, right?
Yeah. Because we're DFSing, there is a property of the way we're handling this that the order that we visit connected components are in reverse topological order. I don't use that fact too much. However, some algorithms do like to manipulate that fact. It is also cleaner to implement using that fact. So that's, I don't think that's strictly required to use. However, it is a nice fact to remember for implementation details. There are also commutation graphs for BCCs for the 2 vertex connect components and 2 edge connected components. And for those ones, we're again eliminating cycles because 2 VCCs and 2 ECCs are cycles. But in a directed graph, an acyclic directed graph is equivalent to a tree. So with these types of condensation graphs, by removing cycles, it allows us to do more unique algorithms since there are no cycles. Does anyone have any questions about that? Yes.
What do you mean by acyclic directed graph is equivalent to a tree?
Sorry,
Undirected.
acyclic undirected graph.
Oh.
That was a misspeak. Any other questions? Alright. So that is all I have for today.